There's a place in southern Iraq, flat, bare, unremarkable from the air, where a structure of baked brick has been sitting in the desert for more than 4,000 years. When archaeologists first dug it out in the late 1920s, they didn't even know what they were looking at. They called it a temple, then a dam, then a water regulator. It took the better part of a century-old excavation photographs, declassified satellite imagery, and fresh fieldwork to confirm the simple thing it had been all along. A bridge, possibly the oldest bridge ever identified anywhere on Earth, and it had been sitting in plain sight for 90 years, while trained experts argued about what it even was. Now, sit with that for a second. We couldn't even recognize it. If you've been with this channel for a while, you already know the pattern. The official version says, ancient people were primitive. Then the data quietly says something else. Hit subscribe if you want to keep pulling on that thread, because this is one of the threads you don't put down easily. 7 ancient bridges. 7 engineering problems the standard timeline struggles to account for. Not fringe theories, not speculation. Materials science, structural physics, and archaeology sitting at the same table and arriving at the same uncomfortable place. 6 of them break the rules we assume about what ancient people could do. One of them, in stone, comes close to breaking physics itself. Let's go through them one at a time. Bridge number 1. And we start in Iraq, because that's where the oldest one is. The Sumerian city of Girsu, near the modern town of Tello in southern Iraq. This was a real city, founded at least 5,000 years ago, eventually the heart of the kingdom of Lagash, a metropolis devoted to the Sumerian god Ningirsu. Thousands of cuneiform tablets came out of the ground here, trade records, administrative accounts, economic ledgers. These were sophisticated people running a sophisticated operation, and they built a bridge. The Bridge of Girsu was raised in the early dynastic period of Mesopotamia. The archaeological and textual evidence points to a construction window somewhere around 2900 to 2600 BCE, with the structure staying in use through later periods into roughly 1800 BCE. Read that again. Over 1,000 years of active service before most of what we casually call classical civilization has even begun. Here's where the timeline problem starts. The bridge was built of baked brick, not raw mud brick, which slumps and dissolves the moment water touches it. Baked brick fired, hardened, deliberately engineered to take repeated hydraulic stress, year after year, flood after flood. The British Museum, which has led the conservation work at the site, together with Iraq's State Board of Antiquities, has described it as a strikingly clever piece of large-scale ancient engineering. That's the assessment of one of the most conservative institutions in the field, not a fringe researcher. The British Museum and staff. For 90 years, the professionals who excavated this site read it as a temple, a dam, a water regulator, everything except the thing it was. It took modern reanalysis to settle it. The official version missed it for a century, and the structure never moved. It was right there the whole time. Coincidence? Possibly. But it's the kind of coincidence that tells you something uncomfortable about the limits of our own interpretive frameworks when we point them at ancient engineering. If we can stare at the oldest known bridge in the world for 90 years and call it a dam, what else are we currently mislabeling? And here's where it gets uncomfortable. Bridge number 2. Greece. Around 1300 BCE. A completely different kind of problem. Picture the Argolis, in the northeast of the Peloponnese. Dry hills, olive scrub, the hard white light of the Greek summer. Running through it is a low stone bridge that, depending on how you define the word, is either the oldest surviving bridge in Europe or one of the oldest arch bridges still in use anywhere on the planet. The Arkadiko Bridge. It was built between roughly 1300 and 1190 BCE. During the late Helladic period, the height of Mycenaean civilization, the same culture that raised the Lion Gate at Mycenae and the Great Citadel at Tiryns. And the bridge is still standing, still crossable. Today, look at the numbers. The structure runs about 22 meters long, more than 5 meters wide at the base, around 4 meters high. It was built in what's called Cyclopean masonry massive, irregular limestone boulders, packed with smaller stones and fragments, fitted together so tightly the blocks slide into something close to a locking grip. No mortar, no adhesive of any kind, nothing holding it together but the weight, the geometry, and the precision of the fit. And it wasn't a footpath. The roadway has raised curbs built into it, deliberate, engineered edges that appear designed to guide wheeled traffic, horse-drawn chariots, along the surface. This was part of a Mycenaean military road linking Tiryns to Epidaros, built for fast-moving vehicles. 33 centuries later, it still works. Local farmers still walk across it. It's been reported to carry the weight of a modern vehicle, a structure engineered for Bronze Age chariots, casually shrugging off loads its builders never imagined. Now compare that to us. Modern bridges, modern overpasses, modern roads, they're typically rated for a service life of 50 to 100 years before they need major rehabilitation. The Arkadiko Bridge is sitting at around 3,300 years, without a single documented repair, no maintenance crew, no rebar, no mortar, no engineering software, still standing. The standard explanation is Cyclopean masonry, corbelling, gravity. And the standard explanation isn't wrong, but it is incomplete, because it doesn't answer the sharper question underneath it. How did builders working around 1300 BCE judge the load distribution precisely enough by eye, by hand, by accumulated craft that a structure with no binding material and no reinforcement would still carry weight 32 centuries later? Their geometry didn't just work, it outlasted empires. That's not primitive. That's a different category of engineering than the one we practice today. But that's not all. Bridge number 3. We stay in Greece, but the question changes. Not durability now, scale and system. Because Arkadiko isn't alone. There are at least 4 known Mycenaean corbel arch bridges in this region, all part of the same Bronze Age road network, stitching together Mycenae, Tiryns, Tolo, and Epidaros, all similar in design, all built in that same window, 1300 to 1190 BCE. 2 of them are still in active use. The others survive as partial ruins. This was not one gifted builder working alone on one lucky day. This was a system standardized bridge engineering, repeated across a regional military highway by a civilization that, according to our neat timeline of technological development, shouldn't quite have that capability yet. The Petrogephori Bridge, crossing the same stream about a kilometer west of Arkadiko, has a longer span and a slightly higher vault than its neighbor. Same chariot curbs, same logic. The road between them is still traceable across the landscape. Here's the question the standard timeline doesn't enjoy. If this level of infrastructure, networked, standardized, deliberately built to carry rated loads, already existed in the Aegean in 1300 BCE, then what else were these people doing that simply hasn't survived? And that's the quiet tragedy buried inside all of this. Stone survives. Rope doesn't. Wood doesn't. Organic material rots away in a few centuries and leaves nothing behind. The archaeological record only ever shows us the hard edges of the past, the stone, the brick, the things fire and water can't erase, the soft infrastructure, the knowledge, the calculations, the methods passed mouth to ear, from master to apprentice, that vanishes completely. And when it vanishes, the textbooks have a word for the gap it leaves behind. They call it primitive. Now, we are not at the core of this yet. Bridge number 4. We move from Greece to China. And this is where the physics stops being a figure of speech and starts being a real, measurable problem. The Fujian region, on China's southern coast, 11th to 13th century, the Song dynasty. Builders here were constructing stone beam bridges, and the spans of those beams were doing something materials science says should not be possible. Let me explain tensile strength in plain terms, because the whole mystery lives in this one idea. Tensile strength is how much pulling force a material can take before it cracks. Push down on a block of stone, and its tremendously strong granite holds up skyscrapers under compression. But bend it, stretch the underside of it, and stone is fragile. Lay a stone beam flat across a gap, and gravity pulls the middle down, which stretches the bottom of the beam, and stone hates being stretched. For granite, the tensile strength, the force needed to tear it apart, runs only somewhere between about 3 and 7 megapascals, depending on the stone. That's a fixed ceiling. Physics doesn't negotiate, which is exactly why, across every ancient civilization on Earth, Egyptian, Greek, Roman, Indian, pre-Columbian, the same unwritten rule held. Stone beams, the horizontal spans that bridge a gap, rarely exceeded about 7 meters of unsupported length. 7 meters was understood, by hard experience, on every continent, as roughly the limit before gravity wins and the stone snaps in the middle. The Fujian bridges routinely used stone beams with unsupported spans of more than 14 meters, and in one surviving case, the Jiangdong Bridge, among the largest stone beam bridges ever built, a single granite beam spans about 21 meters. One stone, 21 meters. That is roughly 3 times the limit that every other ancient culture on the planet independently identified as the safe maximum. A peer-reviewed engineering analysis put the problem bluntly. Stone beams and stone architraves appear in ancient architecture all over the world, and then, as now, their unsupported length essentially never exceeds 7 meters, with the great exception of these megalithic stone bridges in Fujian. 21 meters, in granite, unsupported, still standing. And the official version genuinely struggles here. The current structural analyses say these beams are riding right at the theoretical edge of what granite can physically take. Some researchers think the builders understood something empirical about the specific stone in that region, a local granite sitting at the very top of the strength range. Others suspect a loading or pre-stressing technique we haven't fully reconstructed. Nobody is certain. The beam should crack under its own weight. It doesn't. The physics that should have stopped it didn't. That is not a mystery in the spiritual sense. That is a mystery in the engineering sense. And those are the ones that are actually hard to wave away. But that's not all. Bridge number 5. South America, the Andes, a completely different material and a completely different kind of impossible. The Inca Empire, at its height in the 15th and early 16th centuries, controlled a stretch of territory running through modern Peru, Ecuador, Bolivia, Argentina, Chile, and Colombia, and roughly 40,000 kilometers of road, a network rivaled in the ancient world only by Rome. Armies, trade goods, and relay runners called chasquis moved across it constantly. The problem was the terrain itself, the Andes' vast canyons, roaring rivers, gorges that made a conventional stone bridge impossible across hundreds of critical crossing points. The Spanish who arrived in the 16th century wrote down their astonishment at the solution. The Inca had beaten the canyons with suspension bridges, woven entirely out of grass. Not rope as we'd think of it. Ichu and Kyoya, tough highland grasses harvested, dried, pounded soft with stones, then twisted by hand into thin cords. The cords braided into ropes. The ropes braided into thick cables, each main cable bundled from dozens of smaller strands, then anchored to stone abutments cut into the rock on either side of the gorge. Women braided the fine cords, men braided them up into the great load-bearing cables. The result behaved, structurally, like the cables of a modern steel suspension bridge built from straw. Take the Queshuachaca, the last surviving Inca rope bridge, still hanging over the Apurimac River in southern Peru. It spans roughly 28 to 30 meters across the canyon, a little over a meter wide, dangling about 18 meters above the water. Researchers who've studied it estimate it can hold something on the order of 16,000 pounds. The Smithsonian's own people describe it as comfortably carrying dozens of people, more than 100 at once. And the Inca built over 200 of these. Some larger spans reportedly reached around 45 meters across gaps that Roman engineers would have looked at, shaken their heads, and walked away from. Europe did not develop comparable suspension bridge technology until the 19th century. Think about what that actually means, not as a rhetorical flourish, literally. The first modern chain suspension bridges in Europe date to the early 1800s. Metal, engineered, industrially produced. The Inca were achieving similar spanning distances over live canyons, under load, carrying armies with braided grass centuries earlier, with no metallurgy and no written engineering manuals at all. And here's the detail most people miss. The Queswachaka is still rebuilt every single year by the surrounding communities, using the same grass, the same braid, the same division of labor the Inca used. Around 800 people, 4 communities, 3 to 4 days of work. The tradition was inscribed on UNESCO's list of the Intangible Cultural Heritage of Humanity in 2013, and it has run unbroken for roughly 500 years. You can stand there and watch a 500-year-old engineering method work in real time. Now here's what we still can't fully model: the exact way braided grass behaves under the real loading of a live suspension bridge in a gusting canyon wind over time. Modern engineers have studied the Queswachaka closely. They understand the structure. They still can't perfectly predict how the fiber holds the way the Inca engineered around it by feel and by inheritance. Grass, doing the job of steel, and the knowledge of how to make it work survives entirely through oral tradition and a few hands that still remember. Lay the data points side by side for a second. A 4,000-year-old brick bridge nobody could even identify. A 3,000-year-old stone arch with no mortar, still carrying vehicles. A 21-meter granite beam that should fracture under its own weight, still intact. And a grass bridge carrying army loads across a 30-meter canyon, centuries before Europe had anything close. We're going to keep going, because we are not done. Bridge number 6. Back to China, a different era and a different kind of precision. The Zhaozhou Bridge, also called the Anji Bridge, in Hebei Province, built between 595 and 605 CE during the Sui dynasty, designed by a craftsman named Li Chun. It is the oldest surviving open spandrel stone segmental arch bridge in the world. That's a mouthful, so let's take it apart, because every word in it is doing real work. A standard ancient arch bridge was solid, one big arch, packed with stone above it, holding up the road deck. Heavy. Enormously heavy. Li Chun did something nobody had done. He cut material out of the upper sections of the arch, opening up the spandrels, the triangular spaces between the main arch and the road deck, and replaced that solid stone with 4 smaller secondary arches, 2 on each side. The effect was extraordinary. The bridge got lighter, more flexible under load. Floodwater could pour through those open spandrels instead of slamming into a solid wall. And it was more elegant than anything else of its era. The main span runs about 37 meters of cut and fitted stone. The arch rises only about 7 meters over that span, meaning it's remarkably flat, which cuts down the outward thrust on the supports and lets the bridge stretch long and low in a way that looks almost modern. Here's the number that matters. The Zhaozhou Bridge has been standing for more than 1,400 years. It has ridden out multiple documented major earthquakes, at least 8 significant floods, and the weight of modern traffic. And the design principles it's built on, reducing dead load with open spandrels, lowering the approach roads with a segmental arch, letting the structure flex under dynamic load, instead of transmitting full stress into the main span. Those are principles European engineers were still working out from scratch in the 1800s. Li Chun solved them in the year 605, in stone, 1,200 years early. But that's not all. Bridge number 7. We end where the Roman Empire is at its peak, and where the data turns genuinely hard to explain away. The Alcantara Bridge, in western Spain, crossing the Tagus River. Built around 104 to 106 CE, under the Emperor Trajan, designed by an architect named Caius Julius Lasser. 6 granite arches, nearly 200 meters long, standing some 45 meters above the river, with a central span close to 29 meters, the tallest and one of the most ambitious surviving Roman arch bridges in the world. Here, the official version is comfortable, and rightly so. Romans, legions, Imperial Engineering Corps. We are not going to insult you by pretending the Romans didn't build Alcantara. They did. The inscriptions are right there in the stone. What we want you to look at is what the bridge is made of and what happens to it after Rome falls. Because here's the part that should stop you. The Alcantara bridge is built of massive granite blocks, cut, shaped, and fitted together with no mortar at all. None. Dry stone. The blocks are dressed so precisely that they lock against each other by weight and geometry alone, holding a 200-meter bridge, 45 meters in the air, for 19 centuries, with nothing gluing it together. The Romans were so confident in it that Lasser carved a line into the stone that has aged into something between a boast and a prophecy. I have built a bridge that will last forever. And then history tried to test that claim, hard. In 1214, the Moors destroyed one of the arches. It was rebuilt centuries later, in 1760, and again in 1809 during the Peninsular War. Retreating armies deliberately blew up spans of the bridge to stop their enemies crossing. Each time, the bridge was patched and rebuilt by later hands, with later methods. And here is the uncomfortable observation that engineers and conservators keep running into. The rebuilt sections, the later, post-Roman repairs, are visibly weaker than the original. They wear faster. They fail first. The 1900-year-old Roman granite, fitted without a drop of mortar, consistently outperforms the patches that were bolted onto it 1,000 and even 1,800 years later. The old work outlasts the new work. The same pattern shows up across surviving Roman bridges again and again. The original Roman sections hold, while the modern repairs degrade around them. That's not a theory. That's a documented engineering observation you can go and read in conservation reports. The Romans cut a sign into the stone that said, "This will last forever," and so far, against war, flood, and time, the Roman stone is winning, and our repairs are losing. So we don't know everything about how they did it. We can measure the precision of the cuts. We can see the dry stone fit. We can read the inscription. What we can't quite reproduce is the result granite shaped so accurately, by hand, that it needs nothing to hold it together and outlives every modern attempt to fix it. Now, lay all 7 of them side by side. 1. A 4,000-year-old Sumerian bridge that the experts couldn't even identify for 90 years. 2. A 3,300-year-old Mycenaean stone arch, no mortar, still sound under vehicle loads. 3. A whole network of standardized Bronze Age bridges, pointing to systematic engineering knowledge across an entire civilization. 4. A Song Dynasty granite beam, spanning 3 times the supposed maximum for stone in any culture on Earth. 5. Inca grass bridges, carrying army loads across 30-meter canyons, centuries before Europe had anything comparable. 6. A 7th century Chinese arch, using load reduction principles Europe wouldn't reach until the 1800s. 7. A Roman bridge of mortarless granite that, 19 centuries on, still outperforms every modern repair stitched into it. Here's the inversion. We tell ourselves that ancient history is a story of steady improvement. Primitive to advanced. Simple to complex. Ignorance, climbing slowly toward us, the clever ones at the top. The data from these 7 structures suggests something different and stranger. It suggests that specific, sophisticated, brilliantly functional engineering knowledge appeared sometimes very early, operated at a level we still can't fully match, and then, in several cases, simply disappeared. That knowledge wasn't building a staircase up to us. It was solving problems we still struggle with, by means we still don't fully understand, and then the precise knowledge of how was lost. The question was never whether ancient people were smart. They obviously were. The real question is whether we've correctly mapped what they knew. And what the stone keeps telling us is, we haven't. Not completely. Not even close. We think we're the advanced civilization, looking back at the simple ones. These bridges raise the quieter possibility that we are missing chapters, that there were peaks of specific technical mastery that rose, solved enormous problems, and then vanished, and that what we dig up is only the stone record of those peaks. The grass ropes are gone. The wooden scaffolding is gone. The engineers' notes are gone. The apprenticeships that carried the knowledge are gone. What's left is a 21-meter granite beam sitting in Fujian that, by the physics we can measure, should not still be there. But it is. The official version will tell you there's a mundane explanation for every single one of these. Maybe. But notice what they never do. They never put all 7 on the same table at once, because the moment you do, the story we were taught stops holding together. So I'm not going to tell you who built them. I'm going to do something more uncomfortable. I'm going to show you that the people whose job it is to explain this can't. There's one more category of ancient bridge we haven't touched yet, the submerged ones. Structures dated by geology and marine archaeology to a time when the sea level was far lower than today. Bridges that, if they really were built when the dating suggests, would point to organized construction at a moment when the official timeline insists no civilization capable of it existed. That story has its own video, and the numbers in it are even harder to explain away than anything we covered today.